Hello everyone and welcome back to CodeChef. Now it's time to discuss what happens when multiple transactions run at the same time. In real-world databases, concurrency is unavoidable, which means multiple users are reading and writing data simultaneously. While concurrency improves performance, it also introduces serious challenges. In this video, we will focus on three tightly connected concepts: deadlocks, isolation levels, and concurrency anomalies. Understanding these topics is essential to know why databases sometimes block, abort, or roll back transactions and how they still maintain correctness under heavy load. What is a deadlock? A deadlock occurs when two or more transactions are waiting indefinitely. That means two or more transactions are trying to complete their execution, but none of them is completed. Then each transaction holds a lock that the other needs. That means the data or any other resource is held by each transaction that is needed by the other transaction to complete its execution. And this is what leads to deadlock. For example, transaction T1 locks row A and waits for row B, while transaction T2 locks row B and waits for row A. So let's suppose these are two sources of data, row A and row B. Now both transactions T1 and transaction T2 need row A and row B. But row A is locked by transaction 1, so it cannot be used by transaction 2. And on the other hand, row B is locked by transaction 2 and therefore it cannot be used by transaction 1. So this stops the processing of the whole transaction, leading to a deadlock in the system, since both transactions keep waiting forever. Conditions for deadlock. Deadlock occurs only if all four conditions are present. Now let's see which are these four conditions. First, mutual exclusion. It means resources cannot be shared. Second, hold and wait. So transactions are holding resources while waiting for other resources to complete their execution, just like we discussed in the last example. Rule 3 is no preemption. It means resources cannot be forcibly taken. So we cannot take one resource from a transaction and assign it to another one. Fourth, circular wait. A circular chain of waiting exists. So like we discussed in the last example, transaction T1 and T2 are holding resources which are required by each other, leading to a deadlock in the system. Similarly, in circular wait, there can be two or more transactions which are all waiting for a resource which is held by another transaction, making a circular chain of transactions which are waiting for resources to complete their execution. So we have discussed what are deadlocks and how they occur in a system. But now we are going to discuss how to handle deadlocks. There are three techniques using which databases handle deadlocks. First, deadlock detection. It happens by periodically checking for deadlock cycles and terminate one transaction, which is the victim. So let's suppose there are multiple transactions which are waiting for other transactions to release resources to complete their execution. If we terminate any one transaction, then the resource which is held by that transaction is free. It can be used by the other transaction which is waiting for that resource. So this is a method for deadlock detection. Second, deadlock prevention. We can prevent deadlocks by avoiding circular wait. That means by controlling the execution of such transactions which need similar resources at the same time. And secondly, enforce lock ordering. So we can schedule resources in such a way that each transaction gets the required resource for completing its execution. So we can order the resources in such a way that they are assigned to the transactions in a specific order so that the execution of these transactions can be completed timely. Third is timeout based resolution. It means if a transaction waits for too long, it is aborted. Aborted means that transaction is cancelled. What are isolation levels? Isolation levels define how and when the changes made by one transaction become visible to other concurrent transactions. When multiple transactions execute at the same time, the database must answer three critical questions. First, can one transaction see uncommitted data from another? Uncommitted data means the data that is not saved yet, it is still being processed. Second, can the same query return different results within a transaction? That means if we are running the same query on a single transaction, then is it giving same results or different results every time we are executing it? Third, can new rows appear if the same query is re-executed? So if I'm running the same query again and again, then is it giving me same output or every time I'm getting a different output? Isolation levels provide formal rules to answer these questions. Common isolation levels based on ANSI SQL standard. First, read uncommitted. So this is the lowest isolation level. Why? Because uncommitted data that is not saved by the transaction, is visible to other transactions. That is why it is the lowest isolation level. Second, it allows dirty reads. Dirty read itself means one transaction can read the data modified by another transaction and that data is not yet saved. It is still being modified or still in the process. Third point is rarely used. So because this is the lowest isolation level, so we rarely use it. Second, read committed. This means only committed, only saved data can be read by other transactions. Second, it prevents dirty reads. Third, allows non-repeatable reads. It allows getting multiple different results whenever a query is multiple times executed on a single transaction. Repeatable reads. Same row always returns the same value. This means whenever we are running a query on any particular row, it will always give same output. Then, prevents dirty and non-repeatable reads. Third, phantom reads may occur. Phantom reads means when two same queries are executing but they are retrieving different set of rows. Next is serializable. It is the highest isolation level. In this level, transactions execute as if serialized. That means they are arranged in a proper serial, in a proper order, and this is the safest but slowest isolation level. Concurrency anomalies. Concurrency means when we are executing multiple transactions at the same time. Concurrency anomalies occur when transactions execute simultaneously. First is dirty read. We have discussed about this. It means reading uncommitted or unsaved data from another transaction. Second, non-repeatable read. It means same query returns different results within a transaction. Phantom read. New rows appear when a query is re-executed. So ideally, whenever we are running the same query on same set of data, the output should be same. But in case of phantom read problem, new rows appear whenever a query is re-executed. How to choose an isolation level? Choosing the right isolation level depends on application type. So what is the functionality of your database? Second, performance requirements, and third, data criticality. More critical data a database has, more should be the isolation level for the same. So this concludes our discussion on deadlocks, isolation levels, and concurrency anomalies. We saw that deadlocks are a natural consequence of locking and concurrency. Isolation levels define the rules that control transaction visibility. Concurrency anomalies explain what can go wrong when isolation is too weak. Make sure to practice these concepts on the CodeChef platform because they are frequently asked in interviews, exams, and real-world system design discussions. Thank you so much for watching.